Hi, future teacher. Need a math refresher lesson to get prepared for your teacher certification exam? If so, you found the right spot. By the end of this lesson, you will be totally ready to tackle the probability and statistics questions that you will likely receive on test day. But don't stop here. Get full access to the study guides, video lessons, and practice tests that makes passing your teacher certification exam simple by visiting teacherpreps.com.
In this video, we're going to find the probability of complementary, mutually exclusive, dependent, and independent events. Let's first talk about complementary events. These are two events where when one occurs, the other does not occur, and together their probabilities add up to 1. An example would be flipping a coin. You have 1/2 chance of flipping and getting heads, and 1/2 chance of flipping and getting tails. You cannot flip and get heads and tails in the same flip. And also, when you take 1/2 plus 1/2, you get 1 whole. This brings us to mutually exclusive events. These are two events that cannot occur simultaneously. An example would be rolling a dice. You can't roll a dice and get a 1 and a 6 on the same roll. You'd have to roll it twice to get both of those numbers. Now, the difference between mutually exclusive events and complementary events is that the probability of the mutually exclusive events does not have to add up to equal 1. Now, let's move on and talk about independent probability. Independent probability is a form of compound probability, meaning that more than one event is happening at the same time. With independent probability, the outcome of the first event does not influence the outcome of the second event. The key word on some of the problems is the word replaced. For example, if you're pulling marbles out of a bag and you don't replace it, then the outcome of the first event does influence the second event. So if you don't want it to influence it, you have to replace it. When we have compound probability, you find the ratio of each probabilities and multiply them. Let's go through this example together. It says that you spin the following spinner and roll a fair 6-sided dice. Find the probability of the following. Notice that I have this capital B, and then I have something in parentheses. This is read as the probability of spinning a red and rolling an even number. With compound probability, the key word is the word and. That's telling us that we're going to have 2 events. So as I said, we're going to find the ratio of spinning a red and multiply it by the ratio of rolling an even number. So look at the spinner. What is the probability of rolling a red? There's 1 red out of 3 total. Then think about the numbers on a 6-sided dice. How many of them are even? 3 out of the 6 are even. So now I can take 1/3 times 3/6. That gets us 3/18. Next, we need to simplify. You could divide a 3 out of both the numerator and the denominator. So our probability is 1/6. If I was going to spin the spinner and then roll a dice, we would expect that 1 out of every 6 times you would get a red and then roll an even number. Now pause the video and try this one on your own. Now let's see how you did. It says that we're flipping a coin. What is the probability of flipping a tails 3 times in a row? That means that we're going to have the probability of flipping a tails times the probability of flipping a tails times the probability of flipping a tails. There's 1 out of 2 sides of our coin. So we have 1 times 1 times 1, which is 1, and 2 times 2 times 2, which is 8. The likelihood of flipping tails 3 times in a row is 1 out of 8. So now let's talk about dependent probability. This is when the outcome of the first event does influence the outcome of the second event, and the key word there is not replaced. Let's go through this first problem together. It says that there are 10 yellow, 6 green, 9 orange, and 5 red cards in a stack of cards turned face down. Once a card is selected, it is not replaced. Find each probability. So we want to find the probability of getting a yellow card and then getting a green card without putting the yellow back. How many yellow cards are there? There are 10 yellow cards. How many total cards are there? There are 30 total cards. Then, when you have probability, you want to assume that you get what you wanted on the first event. So we're going to assume we got a yellow card, meaning there's no longer 10 yellow cards in the deck, there's now 9. Now we can do the second ratio. How many green cards are there? There's 6. But instead of being 30 cards, now there's 29 because we did not replace it. When we multiply, it helps to simplify before we multiply. We can divide a 10 out of both 10 and 30, and then you can divide a 3 out of both 6 and 3. 6 divided by 3 is 2, and 3 divided by 3 is 1. So we have 1 times 2, which is 2, and 1 times 29, which is 29. So the probability of getting a yellow card and then a green card without replacing the yellow card is 2 out of 29. In this video, we're going to talk about probability in terms of sample space and equally likely outcomes. The probability of an event states the likelihood that it will occur. You find the probability by making a ratio of the number of favorable outcomes over the number of total outcomes. When you find probability, you need to know what the sample space is. This is all of the possible outcomes. Also, when you find probability, you need to have each outcome to be equally likely, meaning you have to have an equal chance of things occurring. If you looked at this spinner right here, do we have an equally likely chance of getting a 1, 2, or 3? The answer is no. So you could not say the probability of getting a 1 is 1/3. Some examples of equally likely outcomes would be flipping a coin. You have equally likely chances of landing on heads as you do landing on tails. Another example would be rolling a fair 6-sided dice. You have just the same chance of rolling a 1 as you do all the other numbers. Before we find probability, let's first talk about sample space. The sample space is all of the possible outcomes. These first two questions say to list out the sample space for each of the following problems. Let's look at the first one. It says a fair coin is flipped. What do you think the possible outcomes are? You could flip and get heads, and you could flip and get tails. You have a 50-50 chance of getting each. There are two possibilities for this question. The next one says that a marble is pulled from a bag and a coin is flipped. List the sample space. We want both things to occur. We could pull a green marble from the bag and get tails, and we could pull a green marble from the bag and get heads. We could pull a red marble from the bag and get tails, and we could pull a red marble from the bag and get heads. Next, we could pull an orange marble from the bag and get tails, and an orange marble and get heads. We could draw purple and get tails, and purple and get heads. And finally, we can get blue and get tails, and get blue and get heads. So how many outcomes were there? There were 10 possible outcomes. Now pause the video and try this one on your own. Now let's see how you did. It says that a coin is flipped and a dice is rolled. List the sample space. Well, a coin has heads and tails, and a dice has the numbers 1, 2, 3, 4, 5, and 6. We could get heads with 1, heads with 2, heads with 3, heads with 4, heads with 5, and heads with 6. We could do the same thing with tails. So when we flip a coin and a dice is rolled, we have 12 possible outcomes. Now let's take what we learned about sample space and find the following probabilities. The first one says to find the probability that a 6 will be rolled on a fair 6-sided dice. Well, a 6-sided dice has the numbers 1 through 6. Recall that probability is the ratio of favorable outcomes over total outcomes. Well, the favorable outcomes is 1 because we have 1 6. And then we have 6 total outcomes. So our probability is 1/6. Go ahead and pause the video and try this last one on your own. The last one says to find the probability that a red marble will be drawn from the bag. Well, how many red marbles are there? There's 1. And how many marbles are in the bag? there are 5. So our probability of getting a red marble is 1/5. In this video, we're going to talk about the role of a random sample. Statistics is the science of using data to find patterns and infer representations from the samples taken. When taking data on something, we need to know what that data is going to tell us. Data analysis is a process of looking at the data closely and then modeling the data to discover useful information to make better decisions. When we collect data, it's important to have a random sample. This is so that our data set is not biased and truly represents the population that we are collecting data on. Random sample is a randomly selected subset of the population. The key word there is random. If you are collecting data or conducting a survey, there are steps so that you can design a random sample. First, you need to define the population. What group of people are you wanting to be in the population? Are you talking about women, men, people of a certain age group, or people in a certain demographic? After you know your population, you need to choose your sample size. This is how many people that you are going to be surveying. It needs to be an appropriate amount of people to accurately reflect the population. After you choose the sample size, you need to list the population out. Once you list out the population, you're going to assign number values to everybody inside the population. This is so that you can use the numbers to randomly select participants for your survey. When we randomly select participants, one thing you can use is something called a random number generator. You can also use something called a random lottery. Once you have your participants randomly selected, then you can conduct your survey. We're going to go through a few examples where you're going to state whether the sample is random or not. If it's not random, we're going to explain why. This first question says, you survey customers at a mall. You want to know which stores they shop at the most. So you stand at the same entrance and ask the first 10 people who enter the door what their favorite store is. Do you think this is a random sample? The answer is no. Why is this not a random sample? The key here is that you stood at the same entrance of a mall. This could be biased because all those people might be going to the store right at that front entrance. Therefore, you might be missing people who are going to the other side of the mall to enter the stores at that side of the mall. So if you wanted to conduct a survey, you should ask the same amount of people at every entrance. Let's try another one. We're going to state whether it's a random sample or if it's not. And if it's not, we're going to explain why. This says that you want to know the most popular store in town for local college students. You go to the university and get a list of students. You randomly assign number values to the students and then use a number generator to get 400 participants. You then send out correspondence to those 400 participants. What do you think? Is this a random sample? The answer is yes. You randomly assign numbers, you use the number generator, and the number of participants is large. This would be a good sample for a data set. Now pause the video and try this last one on your own. Now let's see how you did. This one says that you want to know if your favorite singer is currently the most popular singer. You decide to poll your 10 closest friends on their favorite singer. Did you think this was a random sample? The answer is no. This is not a random sample. You asked your friends. Your friends are probably going to have the same opinion as you. If you want to make this a random sample, you should poll people that you don't know. You might also want to define your population. Do you want to know if your favorite singer is the most popular in your age group or among all age groups? Among boys or among girls? Locally or globally? These are all questions that you need to answer when designing your survey. In this video, we're going to draw conclusions about a population from a random sample and identify sources and effects of biases. First, let's talk about what an inference is. This is a conclusion found by using evidence and reasoning from a sample. Then we can make a prediction. A prediction is a forecast about a future event. And then finally, we can have an argument. An argument is reasons that support the idea, action, or theory. Let's go through an example where we have to make inferences and predictions based off of a sample. This first one says that Jillian asked a random sample of 500 students at the local university what their favorite restaurant in town was. Of those 500 students, 200 of them said they liked the local pizza parlor. If there are 100,000 students that attend the university, what is a reasonable estimate for the amount of students that would like the same restaurant? The first thing we need to do is set up a proportion. We know that 200 like the local pizza parlor out of the 500 total surveyed. We can make that our first ratio in our proportion. Then we can set up the other side of our proportion. Since we have those that like the pizza in the numerator, we have to keep that in the numerator. And we have the total in the denominator, so we must keep that in the denominator. We know the total amount of students at the university was 100,000, and we want to know what would be a good prediction for how many like the pizza parlor. Now that we've written our proportion, we can solve it by cross-multiplying. We know that 200 times 100,000 is going to equal x times 500, or 500x. When you take 200 times 100,000, you get 20 million, and that still equals 500x. The final step is to get x by itself by doing inverse operation. You have 500 times x, so we need to divide by 500. Now pause the video and take 20 million divided by 500. When we do that, we get 40,000 students. We can make a prediction that about 40,000 students would say they like the local pizza parlor. Now let's talk about the role of biases. This was not a biased sample because it was a random sample. It could have been biased had Jillian stood in front of the local pizza parlor and asked people walking into the parlor if that was their favorite. This would have caused an effect on the answers of the people surveyed. Now pause the video and try this one on your own. Now let's see how you did. It says that 50 randomly selected seniors in high school were asked what they were going to major in. 10 of them said business. If there are 500 seniors, how many would you predict to say they're going to major in business? The first thing you need to do is set up your first ratio in your proportion. We know that 10 students said business out of the 50 total. Then we don't know how many people are going to say business out of the 500 total. Next, we need to cross multiply. We have 10 times 500 equals x times 50, or 50x. 10 times 500 is 5,000. And that equals 50x. Finally, we need to divide by 50 on both sides. That gets us 100 students. So we could predict that at that school, 100 students would say they wanted to major in business. Let's talk about a source of bias. If you went in and only selected seniors that were in woodwork, then that would not be an accurate picture of the whole school. You could also not say that this would work for the whole country. This is only representative of the students at this school. Let's go through one final problem. It says that a school board member randomly surveys 500 community members to see if they will vote yes to the local bond proposal. Of the people surveyed, 75% said they plan on voting yes. What inferences can you make based on this survey? Well, what do you think? Well, we can infer that 75% of all community members will vote yes. We can then predict that the bond will pass on voting day. In this video, we're going to find probabilities using proportions. Probability of an event states the likelihood that the event will occur. If we have the probability of an event, we can then make predictions about what would happen if the event happens multiple times. To find this prediction, we can use a proportion. A proportion is two equivalent ratios. Let's go through a couple examples together. This first one says that a bag has 10 marbles in it. It has 2 blue, 3 green, and 5 yellow marbles in it. Justine is going to randomly select a marble from the bag, and she's going to do this 75 times. What is the best prediction for how many times she will get a blue marble? The first thing we need to do is write the probability of getting a blue marble as a ratio. How many blue marbles are there? There are 2 blue marbles. That's the numerator in our ratio. How many total marbles are there? There are 10 marbles. That's the denominator in our ratio. Now we could simplify this to 1/5, but it's not necessary. The next step is to write the other side of our proportion. Since we have blue in the numerator on the left, we must have it in the numerator on the right. And then since we had total marbles in the denominator on the left, we must have that in the denominator on the right as well. We're going to solve this to get a prediction of how many times we get a blue marble out of 75 total times. We don't know how many blue, so we can use an X. And we're going to have 75 total. Now we can cross multiply and get 2 times 75 equals X times 10, or 10X. 2 times 75 is 150, and that's going to equal 10X. The next step is to divide by 10 so that we can isolate that variable and get X by itself. But what you do to one side, you must do to the other. 150 divided by 10 is 15. So if we drew a marble out of the bag 75 times, we could predict that we would get a blue 15 times. Go ahead and pause the video and try this next one on your own. When you're ready, hit play and we'll see how you did. Now let's see how you did. It says a spinner is labeled with the following letters. What is the best prediction for how many times a spinner would land on a vowel if it was spun 25 times? The first step is to write the ratio for the probability of spinning a vowel. There are 2 vowels, A and E, and there are 10 total letters. On the other side of our proportion, we don't know how many vowels we get, so we can have X vowels. And we're going to be spinning to get 25 letters. Now that we have our proportion filled out, we can cross multiply to solve for that variable. We have 2 times 25 is going to equal X times 10, which is 10X. 2 times 25 is 50, and then we can divide out 10 from both sides to isolate that variable. 50 divided by 10 is 5. So if we spun the spinner 25 times, we would expect to get a vowel 5 times. In this video, we're going to talk about the measures of central tendency. Let's first talk about the mean. The mean is the average of a set of numbers. You find the mean by taking the numbers in the data set, adding them up, and dividing by how many numbers there are. So for example, if I wanted to find the mean of the numbers 2, 7, and 9, I would take 2 plus 7 plus 9 and then divide by 3. 2 plus 7 is 9, and 9 plus 9 is 18. So we have 18 divided by 3. Our mean is 6. Now let's talk about the median. The median is the number in the middle of the set of numbers. The numbers have to be placed from smallest to largest. Once you do that, you can find the middle number by crossing off the one in the front, crossing off the one in the back, and then continuing until you no longer have any numbers to cross off. As you can see, 15 is exactly in the middle. It's the median. We have 3 numbers below 15 and 3 numbers above 15. The example above had an odd amount of numbers, so there was an exact median. But sometimes there's an even amount of numbers and you don't have an exact median in your data set. Look at the numbers 10, 11, 12, and 13. If I cross off one on the front, one off the back, one off the front, one off the back, I'm out of numbers and there's no number in the middle. When this happens, you're going to take the middle 2 numbers and find the average or the mean of those middle numbers. We're going to take 11 plus 12, and then since there's 2 numbers, we're going to divide by 2. 11 plus 12 is 23, and 23 divided by 2 is going to get us 11.5. Notice that 11.5 is exactly in between 11 and 12. That's my median. Next, we have the mode. The mode is the number that appears the most in the data set. I remember this because mode starts with MO and most starts with MO. Look at these numbers below. In this data set, our mode would be 3 because it happens twice. You can have more than one mode. For example, if I had another 5, there would be 2 modes, 3 and 5. Finally, we're going to talk about the range. The range is the difference between the highest number and the lowest number. Difference means to subtract. So we're going to take the highest number minus the lowest number. In our data set, our highest number is 11, and our lowest number was 1. 11 minus 1 is 10. What that means is that there's 10 spaces in between our highest and our lowest number. Now let's put it all together and go through an example. This says that Toady polled his friends to ask how many hours of sleep they got the night before. The data he collected is listed below. We want to find the mean, median, mode, and range of the data set. First, let's find the mean. Remember, when we find the mean, we add all the numbers up and then divide by how many numbers there are. Go ahead and take a moment and pause the video and add all of the numbers up. When you add the numbers up, you should have gotten 48. Then you need to divide by how many numbers there are. There are 8 numbers. So 48 divided by 8, which is 6. Next, we're going to find the median. The first step in finding the median is to put the numbers in order from smallest to largest. When I do this, I like to cross numbers off so I know I don't forget one. First, we have a 4. Then we have 3 5s. We have a 6, 2 7s, and a 9. Now we're going to cross numbers off from the front to the back until we reach the middle. Notice that we have 2 middle numbers. When you have 2 middle numbers, you're going to add them up and divide by 2. 5 plus 6 is 11, and 11 divided by 2 is 5.5. Notice that 5.5 is exactly in between 5 and 6. Next, we need to find the mode. The mode is the number that occurs the most often. Since we had the numbers in order for the median, we can just look at the numbers in order to find the mode. As you can see, there are 3 5s. That's the number that occurs the most often. So the mode is 5. And then finally, we have the range. The range is the largest minus the smallest. Our largest number on the list was 9, and our smallest number was 4. 9 minus 4 is 5. So our range is 5. In this video, we're going to find probabilities using an organized list, tables, and tree diagrams. When we talk about probability, we're talking about the likelihood that an event will occur. The sample space is all of the possible outcomes of one or more event occurring. We can use things such as a tree diagram as a visual representation of all of the outcomes of an event. Let's go through an example together. This first problem says that you're going to try to figure out an outfit to wear. For your shirt, you have a blue shirt, a red shirt, and a green shirt. For your pants, you have black pants, jeans, and khakis. How many possible outfits are there? Let's first go through by making an organized list. You could have a blue shirt with black pants. You could have a blue shirt with jeans, or you can have blue shirt with khaki. We could have a red shirt with black pants, a red shirt with jeans, and a red shirt with khakis. Then we could have a green shirt with black pants, a green shirt with jeans, and a green shirt with khaki pants. As you can see, we have 9 possible outfits. We found the possible outfits by creating an organized list. We started with the blue shirts, then moved on to the possibilities with red shirts, and then the possibility with green shirts. On that last problem, we made an organized list. Now let's make a tree diagram. In this one, we have ice cream choices. You can have small, medium, and large. For flavor, you can have vanilla, chocolate, or strawberry. And then for toppings, you could have chocolate sauce or butterscotch sauce. We could make an organized list, but the more options you have, the bigger the list is going to be. Sometimes the tree diagram is an easier route. The first step is to create your first layer. You have to first choose whether you want small, medium, or large. From there, you have 3 choices for flavor. So off each one of these, we're going to make 3 lines. You could choose vanilla, chocolate, or strawberry on each one of these. And then after that, you have two choices, chocolate or butterscotch. So each one of those then has two choices. Now we can fill it in. You could choose chocolate sauce or butterscotch. And we can do this for each one of our flavors. So going through our list, we could have a small with vanilla with chocolate sauce. We could have a small with vanilla and butterscotch. As you can see, there are many options. When you want to know your total possibilities, count the outermost layer. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 possibilities. Making the tree diagram helped us see all of the possibilities. And these possibilities would be our sample space. We can then use this list to say that the probability of somebody choosing a small vanilla with chocolate sauce ice cream is 1 out of 18. This next one says you're picking out the kind of helmet for your bike from a catalog. You can either have one with face coverings or without face coverings. And then for the color, you can choose between red, blue, green, or purple. I want you to pause the video and create a tree diagram showing all the possibilities. Now let's see how you did. We have with and without the face covering. Then you have 4 choices for colors. We have red, blue, green, and purple on each one of these. So how many possible choices are there? There are 8 choices. In this video, we're going to interpret graphs, tables, and charts that represent data sets. Let's look at this first graph. This is a histogram. A histogram is one of the most commonly used graphs to show frequency distributions. It looks very much like a bar graph, but bar graphs and histograms have some differences. First, the x-axis has numbers instead of categories. Another difference is that bar graphs have gaps between the bars, where histograms do not. This histogram shows the distribution of the ages of people who attended a movie. The x-axis shows the age groups, and the y-axis shows the frequency. Let's answer the following questions about this histogram. The first one says, what age group did the movie appeal to the most? We want to look for which bar goes the highest. This is the highest bar, so we know that the age group that the movie appealed to the most was 26 to 29-year-olds. There were 20 people in this age group that attended the movie. The next question says, how many people between the ages of 22 and 25 attended the movie? So we need to find that bar. If you look, that bar is exactly in between 8 and 12. So we can estimate that to be about 10 people. The last one says about how many more times did the people in the age group of 26 to 29 attend the movie compared to the 14 to 17-year-olds? Well, we had 20 people that attended the movie in the 26 to 29 age group, and we had about 4 people in the 14 to 17-year-old age group. So how many times was it? Well, 4 times 5 gets us 20. So the answer is about 5 times. Now let's move on to a new type of graph. This is a line graph. A line graph is a type of chart used to show information that changes over time. We plot line graphs using several points connected by straight lines. This is a line graph that shows the change in temperature on Monday. Let's answer the questions that follow. This first one says, what is the temperature at 10:30? Well, if you notice, our graph counts by 1 hours, but there are lines in between. The line in between 10 a.m. and 11 a.m. would be 10:30. So, at 10:30, it would be 8 degrees. The next question says, what is the change in temperature from 11 a.m. to 1 p.m.? We first need to find the temperature at 11 a.m. At 11 a.m., it's 8 degrees. Then, we can see that at 1 p.m., it's 20 degrees. To find the change, we can take 20 minus 8. That's 12. So the change in temperature was 12 degrees. Let's move on to a line plot. A line plot can be defined as a graph that displays data as points or X's above a number line, showing the frequency of each value. It is also a great way to see distribution of data. This line graph shows class sizes and the number of times each class size occurs. What is the most common class size? As you can see on the line graph, 28 has the most X's. So therefore, the most common class size is 28 students. The next question asks about range. Range is the largest minus the smallest. Our largest class size is 31, and our smallest class size is 25. So our range is 6 students. The last question says, what is the median class size? When we find median, we can take one off the front and one off the back until we find the exact middle number. So I'm going to go ahead and do that using my line graph. We have one off the front, one off the back, one off the front, one off the back, and we can continue this till we find the middle number. We can see that we have two middle numbers. When you have two middle numbers, you can add them and divide by 2. It won't make a difference in this case because the two middle numbers are the same. So our median is 28 students. Lastly, we're going to talk about a frequency table. A frequency table lists a set of values and how often each one appears. They may include tally marks and totals to show the frequency or the number of times a specific data value occurs in a data set. When I have tallies, the first thing I like to do is add my totals on the right. Now that I've added my totals, we can answer the questions. The first question says, what is the most common form of transportation taken? We can see that more people chose to walk. The next question says, what mode of transportation is taken about twice as much as a car? Well, a car is 4. The keyword here is about. 2 times 4 is 8. Which one is about 8? The buses. So we can say it's the bus. The last question says, how many people were surveyed? To find this, we can add all of the frequencies. When we add 13 plus 7 plus 4 plus 5, we get 29 people. In this video, we're going to investigate patterns of association of bivariate data in scatter plots and frequency tables. First, let's talk about what a scatter plot is. A scatter plot is a graph that shows the relationship between two sets of data. The two sets of data are graphed using ordered pairs. We also need to know what bivariate data means. Bivariate data has 2 variables. When we graph bivariate data, we can see if we have linear association. This is if they show a linear relationship. And then finally, we can use something called goodness of fit. This is really the line of best fit. It can be used to write an equation in order to make predictions. Let's talk about some scatter plot relationships. The first is a positive linear relationship. What this means is as one variable increases, the other also increases. An example of this is the longer you exercise, the more calories you burn. The amount of calories burned increases as the time spent exercising increases. The next kind of relationship is a negative linear relationship. As one variable increases, the other one decreases. An example would be the more you pay on a bill, the lower the balance will be. Next is a nonlinear relationship. What that means is that there is a relationship, but it's not linear. Graphing cubic relationships would be an example of a nonlinear relationship. And then there are scatter plots that show no relationship. An example would be the amount of money in your bank account and how many hours you slept that night. Pause the video and decide whether the following have a positive linear relationship, a negative linear relationship, or no relationship. Now let's see how you did. The first one says the temperature outside and the air conditioning bill. I like to use arrows to help me choose what kind of relationship they have. As temperature goes up, so is the air conditioning bill. So we have a positive linear relationship. The next one says shoe size and age. As your age increases, your shoe size is also probably going to increase. So this one is also positive linear. The third one says the ink in your pen and the words written. Well, the more you write, the less ink is going to be in your pen. So because these go in different directions, you're going to have a negative linear relationship. And the final one says your hair length and your IQ. This one is no relationship. You can have long hair and have a high IQ, or you can have short hair and have a high IQ. The following table shows ice cream sales given the temperature outside. Let's graph the following data and then find the line of best fit. The first step is to label your graph. I put temperature on the x-axis and I counted by 2s. Then I put sales on the y-axis and I counted by 50s. After your graph is labeled, you need to plot the points. Now that we have the points plotted, we can see that we have a positive linear relationship. As temperature increases, our sales go up. Now we need to create the line of best fit. When doing this by hand, you're just going to try to get in the middle of all the points. Your goal is to estimate a straight line that goes through the majority and the center of the points. And now we have the line of best fit. Once you have your line of best fit, you can write an equation. This equation can be used to make predictions. In this video, we're going to find probabilities of simple events, and we're going to write them as ratios, decimals, and percents. Probability is the likelihood that an event will occur. You may have heard things such as, there's a 75% chance for rain. That's probability. It will likely rain, but there's still a 25% chance that it won't rain. When you find probability, you find it first by writing the ratio that is composed of the number of favorable outcomes over the number of total outcomes. These ratios can then be turned to decimals and percents. Before we learn how to find probability, let's take a look at this scale. At the very left, we have a 0 chance of the event happening. That means that the event is impossible. As you move right on the scale, the chance of the event occurring increases until we hit 100%, or certain that the event will occur. Notice on the scale that we have probabilities written as ratios, decimals, and percents. The ratios and decimals range from 0 to 1, and the percentages range from 0 to 100%. When we have something like 25%, that means that we have a 25% chance that it will happen and a 75% chance that it won't happen. Let's go through a few problems where we have to find the probabilities of events occurring. The first problem says that you roll a dice that's numbered 1 through 20. Find the probability of each event and write them as a ratio, a decimal, and a percent. The first thing I like to do is list out the sample space. The sample space is all of the possibilities. Listing out the sample space can help us determine the favorable outcomes. Notice that we have this P and then we have something in parentheses. That's read as the probability of an even number. Also, remember that probability is the number of favorable outcomes over the total number of outcomes. So we want to start by writing our ratio. How many even numbers are there? We have 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. How many is that? That's 10. And how many total possibilities are there? There's 20. Now we can simplify 10 over 20 to equal 1/2. That's our probability as a ratio. When we write our ratio as a decimal, we can divide. 1 divided by 2. When you divide that, you get 0.5. Now we have it as a decimal. And then finally, to write a number as a percent, we're going to times it by 100. Or we can move the decimal place 2 places to the right. When we move our decimal 2 places to the right, we get 50%. So we have our number as a fraction, a decimal, and a percent. The next one says to find the probability of a 2 or a 20. In this problem, the 2 and the 20 are both favorable outcomes. We have 1 2 and 1 20, so we have 2 favorable outcomes. And then we have 20 total outcomes. 2 over 20 simplifies to 1 over 10. We can write that as a decimal by dividing 1 divided by 10. That gets us 0.1. And then you can move the decimal place 2 places to the right to get 10%. So we have our fraction, decimal, and percent on that one. The next problem says that we want a prime number. A prime number has exactly 2 factors, 1 and itself. 1 is neither prime nor composite. So we have 2, 3, 4 is not because you can take 2 times 2, 5, 7, 11, 13, 17, and 19. How many is that? That's 8. So we have 8 out of the 20 numbers. We can simplify that by dividing 4 out of both numbers. That gets us 2 over 5. To turn it to a decimal, we can divide, which gets us 0.4, and then move that decimal place over to get 40%. So we have our fraction, our decimal, and our percent. Go ahead and pause the video and try this one on your own. Now let's see how you did. It says that John has a spinner with 10 equal sections labeled with the following letters. Find the probability of the following if he spins the spinner once. We want to write the probability as a ratio, a decimal, and a percent. We want to know what is the probability of getting a capital letter or a B. First, we need to figure out how many favorable outcomes we have. We have A, B, C, E, F, H, I, and J. That's 8. So we have 8 of the 10. We can then divide a 2 out of both to get 4 over 5. That's our fraction. To make that a decimal, we can take 4 divided by 5. That gets us 0.8. And then to turn it to a percent, you can move the decimal place 2 places to the right to get 80%. In this video, we're going to represent data through graphs, tables, and charts. Charts and graphs are visual representations of data. They are extremely important and useful as they allow us to analyze data. They also allow us to convey messages or emphasize a point. In addition, charts and graphs allow us to show data in a way that's easy to understand and remember. There are many different charts and graphs. In this video, we're going to talk about 3: histograms, stem and leaves, and line graphs. This first question says that the frequency table shows the ages of people riding a roller coaster. Display the data in a histogram. A histogram is one of the most commonly used graphs to show frequency distributions. It looks very much like a bar graph, but bar graphs and histograms have some differences. First, on a histogram, the x-axis has numbers instead of categories. Another difference is that bar graphs have gaps between the bars, where histograms do not. The first step in creating your histogram is to label the axes. On the x-axis, I've labeled the ages categories. And on the y-axis, I've counted by 5s and labeled that axis frequency. And then finally, I made a title for our graph. The next step is to go ahead and make our bars. Remember that our bars are going to touch, unlike a bar graph. In our first age group, 10 to 19, we have 18 people. So that's going to be just under 20. In our next age group, 20 to 29-year-olds, we have 14, so just under 15. Our next age group, which is 30 to 39, has 12 people, so just above the 10. There are 7 people in the age group of 40 to 49-year-olds, and then there were 3 people in the age group of 50 to 59. Now we have our histogram. What do you notice about the frequency of the roller coaster riders when looking at their ages? We can see that the amount of roller coaster riders decreases with the older age groups. And the age group that had the highest frequency was 10 to 19-year-olds. The next problem says that the following list shows the scores on the last science test. Create a stem and leaf plot. A stem and leaf plot helps us organize data. It allows us to see the distribution of the data because the numbers are listed in order from smallest to largest. This helps us easily see the mode and the median. A stem and leaf plot is a special table where each value is split into a stem, which is the first digit or digits, and a leaf, which is usually the last digit. The first step is to determine which values are our stem. The lowest value is 67, and the highest value is 100, so our stems are going to be 6 through 10. Now that we have our stems made, we can fill in our leaves. The leaves have to be in order from smallest to largest. The first step is to find all the scores that have 6 as a 10 value, or are in the 60s. We only have one, 67, so we can plug a 7 for our leaf. That stem of 6 and the leaf of 7 makes the number 67. The next step is to look at all the scores that are in the 70s. We have 3 scores that are in the 70s, and we have to put them in order from smallest to largest. We have a 3 for 73, a 5 for 75, and an 8 for 78. Now we need to look at all of the 80s. We need to now put these from smallest to largest. The smallest is an 82, and I have 3 of them. You have to put that 2 3 times, 1 for each of the numbers. Then we have an 84, an 86, and an 87. Go ahead and pause the video and finish the rest of the stem and leaf plot. Now our stem and leaf plot is complete. We can use this to see that our mode is 82, because that's the number that occurs the most. We could also sit here and find the median by taking 1 off the front, 1 off the back, 1 off the front, 1 off the back, and all the way until we get to the middle number. We have 2 middle numbers, 84 and 86. In between 84 and 86 is 85, so we know our median is 85. Stem and leaf plots can be very useful when organizing and analyzing data. This last problem says that the following data shows the revenue of a bike store for the first 6 months of the year. Graph the data in a line graph. A line graph is a type of chart used to show information that changes over time. We plot line graphs using several points connected by straight lines. The first step is to label our graph. I've labeled the months on the x-axis. Then I labeled the y-axis, revenue in thousands, and I counted by 0.5. And then I labeled our graph. Now we can plot our points. In month 1, we had 2.4. That's just under 2.5. In month 2, we had 3.1. That's going to be just above 3.0. In month 3, we had 1.8. That's just below 2.0. In month 4, we had 2.1. In month 5, we had 2.7. And in month 6, we had 2.9. Now we can connect our dots. And we have our line graph showing the sales in the first 6 months of the year. What month had the highest revenue? The second month did. What month had the lowest revenue? The third month had the lowest revenue. By plotting our data in a line graph, we can easily see the change in revenue over the 6 months. In this video, we're going to talk about simulations and experimental probability. A simulation is a way of collecting probability data using actual objects such as coins, spinners, and cards. What this means is you might flip a coin 50 times to see if you truly get tails half of the time. Experimental probability is the results of conducting an experiment with probability. Many times, you'll do a simulation to see if your experimental probability matches the theoretical probability. Let's go through the following problem together. It says that the bar graph shows the results from spinning a spinner 200 times. Compare the theoretical and the experimental probabilities of the following. Spinning a 4. Theoretical probability is what we would expect to get. If we look at the spinner, there are 5 sections on the spinner labeled 1 through 5. There's 1 4 out of the 5 sections. So in theory, we would expect to get a 4 1 out of 5 times. When we compare theoretical probability to experimental probability, it helps to turn into decimals and then into percents. You can make 1/5 a decimal by taking 1 divided by 5. That's 0.2. And then 0.2 is 20%. So we should expect to get a 4 20% of the time. Now let's look at the experimental probability, which are the results we got when we spun the spinner 200 times. When we spun the spinner 200 times, we got a 4 37 times. So our experimental probability was 37 out of 200. Again, when we compare, we're going to want to make that a decimal and then a percent. When you take 37 divided by 200, we get 0.185. As a percent, that's 18.5%. So now let's compare what we got in our experimental probability to what our theoretical probability is. We were only 1.5% off. So our experimental probability was pretty close to the theoretical probability. Let's go through another one together. It says that a fair 6-sided dice is rolled 50 times. The results are recorded in the frequency table below. It says to compare the theoretical probabilities to the experimental probabilities. The first one says rolling a factor of 6. Let's find the theoretical probability first. A factor of 6 is a number you can divide out of 6. That would be 1, 2, 3, and 6. There are 4 factors of 6, so our theoretical probability would be 4 out of the 6. To turn that into a decimal, we would have 0.667, and that as a percent would be 66.7%. Now let's look at what we got experimentally. We had 6 1s, 8 2s, 10 3s, and 8 6s. We need to add up how many times we rolled a factor of 6. When you add those numbers up, we get 32, and we rolled it 50 times. To turn that into a decimal, take 32 divided by 50. That's 0.64. So we got it about 64% of the time. In theory, we should have gotten it 66.7% of the time. Our experimental probability was not far off from our theoretical probability. I'll pause the video and try the next one on your own. It says rolling a composite number. Now let's see how you did. A composite number is opposite of a prime number. A prime number has exactly 2 factors, 1 and itself. A composite number has more than 2 factors. So the numbers that have more than 2 factors are 4 and 6. In theory, we would expect to get a composite number 2 out of 6 times. That would be 0.333, or around 33.3%. In our simulation, we had a 4 8 times, and we had a 6 8 times. So we rolled a composite number 16 out of the 50 times. 16 divided by 50 is 0.32, which is 32%. So in our experiment, we rolled a composite number 32% of the time, and in theory, we should have gotten it 33.3% of the time. Our experimental probability was pretty close to our theoretical probability.